Next, integrated rate equation of zero order and first order reaction. Integrated rate equation of zero order reaction. Next, first order reaction after this. So, zero order reaction. For example, if we consider a general reaction, A gives products. You know that zero order reactions does not depends upon the concentration of reactants. That's why we can write rate is equal to K into A to the power 0. Okay. So, for zero order reaction, after time t, we can write rate constant K. K as initial concentration minus final concentration by T. Okay. So, here initial concentration minus concentration at time T by T. So, difference between this initial concentration and concentration at time T, that is indicated with the X. Okay. So, we can write K is equal to X by T. So, integrated rate equation for zero order reaction, K is equal to X by T. Okay. So, what is C naught here? Initial concentration. And C is concentration at time T. Okay. And C naught minus C is X. Okay. So, X by T. So, that is the integrated rate equation for zero order reaction, where this type of reactions does not depends upon the concentration of reactants. Then coming to integrated rate equation. Integrated rate equation for first order reaction. So, both are important. Integrated rate equation of zero order and first order reaction. So, here integrated rate equation for first order reaction. For example, if we consider a reaction, A gives products. Initial concentration of A reactants is small a. Okay. And concentration of products is 0. After time t, okay, we get X moles of products. Okay. And number of moles of reactants left is A minus X. Okay. So, at time t, concentration of reactants is equal to A minus X. Okay. So, we can write rate of the reaction at time t now. Okay. So, rate of the reaction at time t. So, that is equal to dx by dt. So, what is rate of reaction? Change in concentration in unit time. Okay. So, that is equal to K into A minus X. Why? Because rate of reaction depends upon the concentration of reactants. Okay. So, what is K here? Rate constant. Okay. Now, we can write the same equation as dx by A minus X. That is equal to K into dt. Okay. K into dt. What is K here? K is rate constant. Rate constant, which is also called as specific rate. Okay. Then on integration, so we can write this equation as dx by A minus x is equal to k into dt. Okay. So, on integration, this equation, we get minus ln a minus x, that is equal to kt plus I. Okay. So, here I is constant. So, to know the value of I, we must take the initial conditions now. So, initially x is equal to 0 and t is also 0. X is 0 and t is 0. So, by substituting x and t in this equation, we get minus ln a is equal to I. Okay. So, minus ln a minus 0 is equal to k into 0 plus I. Okay. By substituting this, finally we get minus ln a is equal to I. Okay. So, this is I value. What is I value here? Minus ln a is equal to I. Then substitute I value in this equation. Okay. So, we get minus ln a minus x is equal to kt minus ln a. Okay. So, by substituting I value, you can take this as equation 1. In equation 1, we get minus ln a minus x is equal to kt minus ln a. Okay. Now, we can write this as kt is equal to ln a by a minus x. And from this, k is equal to 1 by t ln a by a minus x. Then in log form, we can write the same equation as k is equal to 2.303 by t log a by a minus x. Okay. So, this is integrated rate equation for first order reaction. Okay. So, this is called integrated rate equation for first order reaction.